Namaste. Welcome to this PABSON Distant Learning Education Program, collaboration with Janata Television, live from the studio of Janata Television. And this is grade 10 science. And in last class, we have discussed about this Pascal's law. And today, we will continue with this Pascal's law. Last time we have discussed the statement of Pascal law and some applications of Pascal law. So today we will discuss about some numerical problem related to the Pascal law. So there is one question on the screen. So the question is like this. The figure is given here also. You can see on the screen also. And the question is we need to calculate the pressure exerted on the piston A, and also we need to calculate the weight that can be balanced on the piston A, and also we need to calculate the area of piston C. So let's calculate these findings. Okay. So firstly, the question is here. This is piston A, piston B, piston C, and piston D are there. The cross-sectional area of piston A is there 20 centimeters square, piston B 10 centimeters square, and the force applied on it is 125 Newton, and this piston C is there, the force applied on it is 375 Newton is there. So firstly, let's calculate the pressure exerted on piston A. So let's see here, the cross-sectional area of piston B, cross-sectional area of piston B, let's say it is cross-sectional area is A1. Let's represent this. Area is given 10 centimeter square. So this centimeter square is there. Let's change this into the meter square. That is 10 divided by 100 into 100. So this is in the meter square, right? And similarly, the force in piston B, force on piston B. So this one, let's write down this F1. So force is given over there 125 Newton, right? And we need to find the pressure, force on piston A. So let's write down this cross-sectional area, cross-sectional area of piston A. This one is, let's say A2, that is given 20 centimeters square. So this one is 20 divided by 100 into 100. This is meter square, right? And similarly, we need to find force in piston A. That is F2 equals to what? We need to calculate. So this one is this 0 and 0 cancel. That means this is 10 to the power minus 3 meter square. So let's write down like this. And this one is this and this is cancel. So 2 into 10 to the power minus 3 meter square. Now we have the formula from Pascal's law. So from Pascal's law, the pressure exerted on this piston and the pressure exerted on this piston, they are equal. That means we can write down this F1 by A1 is equal to F2 by A2. So this is pressure exerted on piston B, and this one is pressure exerted on piston A. That is equivalent according to the Pascal's law. So let's put the value of these. Let's write down here. This one is F1. We have this 125 Newton, and A1 is there 10 to the power minus 3, right? And F2 is there. F2 is there. This one we need to calculate F2, and A2 is there 2 into 10 to the power minus 3. So if you calculate this, then F2 equals to, so let's multiply this. Okay, this one is 125 into 2 into 10 to the power minus 3, and that is divided by 10 to the power minus 3. So this will be 250 Newton, 250 Newton. Therefore, the force exerted on the piston A is 250 Newton. Okay, and similarly, we need to calculate the weight that can be balanced on the piston A. So whatever force is there, the same amount of weight can be balanced on this piston A, and we need to calculate the cross-sectional area on this piston C if the force exerted is 375 Newton. So let's calculate this one. Okay, so this cross-sectional area is as it is, and force in piston B, that is F1, I will write down, and this one is 125 Newton. And similarly, the force in piston C, so I will write down this F3 because F2 I have mentioned for this A, piston A. So this F3 is 375 Newton is there, right? And cross-sectional area we need to find. Cross-sectional area for this piston C, for piston C, that is A3 equals to what? Again we have from Pascal's law, and then we have F1 by A1 equals to F3 by A3. This is from Pascal's law. So let's put the value of these. F1 is there 125 divided by area is 10 to the power minus 3 equals to F3 is there 375 Newton, and A3 we need to calculate. This is A3. So if you simplify this, then A3 equals to 375 into this one is 10 to the power minus 3 divided by this 125. So let's simplify this. This is 375 multiply by 10 to the power minus 3 equals to, and divide by 125. So it gives the answer. Therefore, area of this piston A3 equals to 3 into 10 to the power minus 3. This is meter square. So there is 10 to the power minus 3 is there. You can convert this into the centimeter square also by multiplying by 100 into 100. So in this process, we can calculate the numerical problem related to the Pascal's law. So one more numerical problem is there. Let's check. So you can see the question there in the screen also. And the question is like this. In the hydraulic machine, the area of small piston is 50 centimeters square. That of the large piston is 5 meter square. If an effort of 20 Newton is applied on the small piston, how much load can be lifted on the large piston? Okay, so let's see this numerical problem. So here, this second numerical problem. So here, the area of small piston is given here. Area of small piston. So I will represent this by A1. Area is A1. So there is given 50 centimeter square, 50 centimeter square. And the area of large piston is also given over there. Area of large piston. So this one is, if I represent this by A2, then it is given that 5 meter square. And effort or force in small piston You can write down this effort also, no problem, right? So this is given 20 Newton, and load or force in large piston. So this one is F2 equals to what? So we need to find the load that can exert on the large piston, or also we can say force in the large piston. F2 equals to what? So before solving this, we need to check either all the system of unit are in the same system of unit, that we need to check. Okay, so that means this centimeter square is there. This is area of the small piston is given on the centimeter square, and the area of large piston is given on the meter square. That's why we need to convert this both in the same system of unit. That's why I will convert this centimeter square into the meter square, so that the system of unit will be similar one. That means, so how to convert this centimeter square into meter square is 50 is there, and centimeter square change into meter square is divide by 100 and 100. That is divide by 100 into 100. There is 2 centimeter square is there. That's why we need to divide this by 2 times. Okay, that is this is meter square. So this and this cancel. Therefore, we can write down this 5 into 10 to the power minus 3 meter square. Now this is meter square, and this also meter square, same unit. So we can simplify this. Okay. Now again, this is applications of Pascal's law. It is a hydraulic machine, so we can use the Pascal's law formula. So now from Pascal's law, that is F1 by A1 equals to F2 by A2, right? So let's put the values of these. So F1 is, we have F1 here 20 Newton, and A1 is here. A1 is 5 into 10 to the power minus 3, and F2 we need to calculate, right? And this A2 is there 5. So let's simplify this, or F2 equals to 20 into 5 divided by 5 into 10 to the power minus 3. So let's multiply this one. 20 into 5, it is 100. So this is 100 divided by 5 into 10 to the power minus 3, right? So 100 divided by 5 into 10 to the power minus 3. It gives the answer 20,000. Therefore, F2 equals to 20,000. So it is a force. That's why the unit is Newton. That means when we apply the 20 Newton force in the small piston having the cross-sectional area 50 centimeters square, then the force exerted on the large piston of cross-sectional area 5 meters square is 20,000 Newton. So this is also applications of Pascal's law. So by this process, we can calculate the numerical problem related to Pascal's law. Okay, so I think you have got the idea to solve this numerical problem related to the Pascal's law. Now let's move on to density and upthrust. Okay, so what is upthrust? Let's see. Whenever we put some object in the water, okay, for example, let's take the well. If we pull the water, bucket of water from well, then we can easily pull the bucket of water inside the water, right? Bucket can be easily pulled inside the water. But as soon as it will be in the air, then it will be a little bit, we feel difficult to pull. That means whenever the object is inside the water, then some amount of force is exerted by that water to the object. That upward force exerted by the liquid to an object which is wholly or partially inside the water is called the upthrust. So upthrust, it is the upward force exerted by the liquid when the object is wholly or partially inside the liquid. That upward force is called the upthrust, right? And upthrust, it's being force, it is measured in Newton. Being force, the unit of upthrust is Newton, right? And similarly, we can measure the upthrust. So just previously I have said, whenever we lift the water bucket inside the water, then we feel easy, and whenever it is in the air, then we feel difficult one. So whatever difference is there, that difference is the upthrust, right? So we can write down like this. So upthrust equals to real weight minus apparent weight. So what is this real weight and what is this apparent weight? Let's see. So when we measure the weight of an object in the air, then that is called the real weight. The weight measured in the air is called the real weight, and the weight which is measured on the liquid, inside the liquid, then that is called the apparent weight. And the difference of this real weight and the apparent weight is known as this upthrust. If you represent the symbol upthrust by U, then U equals to real weight minus apparent weight. That is about the upthrust, right? So let's see the density. Density, so when you lift the iron, we feel heavy, right? And when you lift up the wood, it will be lighter. That means density, it is the mass per unit volume, right? So density can be defined as the ratio of mass and the volume. That means mass by volume. So if you represent this density by d, small d can be used for representing the density. Also we can use rho also, right? Rho also we can use, and the small d also we can use for the representation of density. And this density is equivalent with mass m by volume v. And the unit of this density is, unit of mass is kg, and the unit of volume is meter cube in SI system of unit. That's why the unit, SI unit of density is kg per meter cube, and in CGS system of unit we can measure that on the gram per centimeter cube. So this gram per centimeter cube is the CGS system of unit of density, whereas the kg per meter cube is the SI unit of density that can be measured one. So some of the standard density is listed on the screen. You can see over there. The standard density of water, it is 1000 kg per meter cube or 1 gram per centimeter cube. That is the standard density of a water. Similarly, you can see the different densities over there. For example, the heaviest metal, that is gold, right? And its density is 19,300 kg per meter cube, or in gram per centimeter cube it is 19.3. Similarly, mercury 13,600, lead 11,000, iron 8,000, common salt 2,170, and aluminum 2,700, sugar 1,590. So they are the some standard density of the substance. And remember that the different substance, they have the different densities. That's why if you take the equal volume of the object, of the different object, then the mass will be different one. If you take the same amount of mass of the different object, then the volume will be vary one. That is due to this different object, they have the different densities. Okay. Similarly, ice 920. So ice, wood and kerosene, they have the less density than the water. That's why whenever we put the ice in the water, it will float in the water. That is about the density. Now relative density is there. Relative density means it's a comparison of the density with the density of water at the 4 degrees centigrade. That means the ratio of the density of substance to the density of water at 4 degrees centigrade is called the relative density. What I mean is the comparison of density of the object with the density of water at 4 degrees centigrade, it is called the relative density. Okay. For example, the relative density of ice is 0.92. That means it is 0.92 times heavier than the density of water at the 4 degree centigrade. That is the relative density. Now, let us see the relations of density and the upthrust. So, you can see in the video over there, one video is there. It is about the relations of density with the upthrust, right. What is given over there is when the egg is kept in the pure water, then it will sink in the water, right. But if you add some amount of salt over there in that same water, and if you again put the same egg over there, then it will float, right. What that mean is, whenever the pure water is there, the density of water is less than the density of water is less than the density of egg. That is why it will sink in the water. The egg will sink in the pure water because the density of water is less than the density of a egg. But whenever we add some amount of salt in the pure water, then the density of water get increased due to the salt, right. And in that condition, when the density of the water, salty water or salt solution we can say, is more than the density of egg, in that condition egg will float. So, what conclusion we can draw from here is the upthrust is directly proportional to the density. If there is less density is there, less upthrust is there. If there is more density is there, then more upthrust is there. So, the density upthrust, it is directly proportional with the density of a substances. So, I think the relation also you are clear about this upthrust and the density. Now, next one, let us see this Archimedes principle. So, Archimedes principle, what the Archimedes principle says, let us see. When the object, suppose this object is here, when this object is wholly or partially immersed in the liquid. Okay. Once again, when the object, this object or a body is wholly or partially immersed in the liquid, then it experiences an upward force, which is called the upthrust, right. It experiences the upthrust, which is equal to the weight of liquid displaced by it. That is the statement of Archimedes principle. Let me remind this again. So, when this object is wholly or partially inside the liquid, it experiences an upthrust, which is directly proportional, which is equivalent with the weight of liquid displaced by it. That is the statement of Archimedes principle. So, in mathematically we can write down the upthrust exerted on that object when that object is wholly or partially immersed inside the liquid, that is equivalent with the weight of liquid displaced by it. This is the Archimedes principle. The upthrust exerted on the object when the object is kept wholly or partially inside the water, that will be equivalent with the weight of liquid displaced by it. This is the Archimedes principle. So, in mathematical form we can write down this weight equals to this upthrust equals to weight of liquid displaced by it, and also we can write down U equals to rho z v. This also mathematical form of this Archimedes principle. Okay, and this upthrust we can measure with the help of this density, acceleration due to gravity, and the volume of object. With the help of this also we can calculate this upthrust. So, let us shortly derive this upthrust, okay, mathematical form of upthrust. Okay. So, for this let us take a one container, right, and then we will take the one object here inside this container, right? And we will feel the water. Okay, so we will feel the water. So let's say this height of the upper surface of the object from level of water is h1, right? Similarly, the height of the lower surface of this object from the surface of water is, let's say, h2. So this one is h1 and this one is s2, and the height of this object is, let's say, h. Okay, now generally the force or the pressure, right, the force exerted on these two surfaces, they are equal and opposite. That's why they get balanced here. Okay, the force exerted here and the force exerted here, that is equal one, right? But the force exerted here and the force exerted in this place, they are different one, and the difference of this is calculated as a upthrust. So I will write down shortly: the force exerted at upper surface. So if I write down this F1, then pressure is force per unit area. That means force equals to pressure into area. So this force we can write down here, P1 into A. The cross-sectional area is same, that's why we can represent by the same A, right? Or so this is liquid pressure exerted at the upper surface of this object. So can I write down like this? F1 equals to, this is rho z and h1, because this height is h1 is there. So we can write down this h1, and this A is as it is. So this I will write down as equation 1. Similarly, the force exerted at the bottom of this object, if I represent that by F2, so force exerted at bottom surface, right? Surface, if I represent by F2, then that is P2 into A, right? This is pressure exerted at the lower surface, and the height of this is S2 is there. So we can write down here, or F2 equals to, this is rho z, and this one is H2 into A. So I'll write down this equation second. So if you subtract this equation second and equation first, that is the upthrust. That is, net force is F2 minus F1 equals to rho z S2A minus rho z H1A. So let's simplify this. This is, we can take the common rho z and A, we can take common. Remaining is H2 minus H1, and H2 minus H1 is this height of the object. That is, this F2 minus F1 we can represent as upthrust U equals to, this one is rho z A into H. This H2 minus H1 is A. Okay, because S2 minus H1 is H, right? Or U equals to rho z, A into H is V. This is volume of a object or volume of a liquid displace also we can say. So, and if we need to prove the Archimedes principle, then so here this is formula, and for Archimedes principle this is upthrust equals to, so this G is as it is, and this one is density into volume, right? This is density of liquid, and this one is volume of object, which is equals to the volume of liquid displaced. That means we can write down this upthrust equals to Z into M. Therefore, upthrust equals to weight of liquid displaced. So this is theoretical proof, and in upcoming class we will discuss about the experimental verification for this Archimedes principle. So thank you very much for joining this class. Thank you very much, everyone.